you can think of the actual or truth, the ground truth, to be either positive or negative. In our case, some people will belong to the diabetic group. Some people will belong to the healthy group. But then, so this will be here. But then, predicted could be P and N. Right? Now, if somebody is diabetic, and our logistic regression says it's diabetic, is that good or bad?
Yes.
That's good, right? That's good, right? So this one is called true positive. And then if somebody is diabetic, but then our logistic regression says, I predict that this person is healthy, is that good or bad? That's bad, right? So that's called false negative. Okay, the prediction is false, right? This one, not diabetic, but then predicted as diabetic, so there'll be false positive, and this will be false. No, this will be true negative. Okay. Obviously, you want these two values to be good and these two to be bad. Right? So let me give you an idea by saying there's certain tests like something scary like cancer. Cancer. You do some test and the test says you have cancer, and sometimes the test will say you don't have cancer. So it could be that positive, negative, this is just a pretend, not actual data. Let's say you have many people going through this test and it says over here 96 people were negative and the test comes out as negative because most people don't have cancer, so good. But you know, like you might have something like 10 people who actually have cancer and does have cancer, right? It is predicted to be to have cancer by this test, right? Okay. What would this be? Can you explain what this one is?
False positive. So you take the test and it shows up positive, but you actually don't have it.
Right, right. You don't have cancer, but this test says you have cancer. And unfortunately, maybe it's like something like 5 people. Okay. And then you might have another person, another group of people who does have cancer but says no, something like 3 people. Now, accuracy in this table is defined as just simply true positive, true negative. How many you got right out of the entire group? Okay, so out of everything. So yeah, just you add up everything. That's called accuracy. Now, what's that in this case? It's like 106 divided by 8, 104, 114? Can somebody type this on your Python and tell me what it is?
0.93.
0.93?
Yeah.
So now your doctor's going to say, oh, this test is 93% accurate, right? Sounds pretty good, right? And then it says, oh, and you have cancer. Right? Okay, so that's like, yeah, you'll be very, very sad and alarmed, right? But in this test, if you have cancer, does that mean that it's 93% sure that you have cancer? Is that what it means?
Yes.
No, it doesn't mean. What's the actual percentage you'll have cancer? The test came out a positive, right? But look at this. What's the actual percentage?
Or like 10.
60, yeah, no, 5 out of 15, which is, no, 10 out of 15, which is 67%, right? So, although this test is 93% accurate, if the test comes out as positive, does that mean you have cancer? What's the likelihood? It's only 66.67. It's not like 93%. This value is highly misleading, right? So that's why we have this confusion matrix, because often you only see the accuracy reported, but it really doesn't do justice to what's really happening. So there are very many different values associated with the confusion matrix, which is that if you have TP divided by TP plus Fn, this is called recall. And then if you have TP plus TP over TP plus FP, this is called precision. And there are very many different names that these go by, but these are the ones that machine learning people use a lot. When it comes to health sciences, they use a different name for this one. They still use precision, but they use sensitivity for this one. Which makes a lot of sense because I raised it, but this will be the people who actually have cancer, right? And if the sensitivity is low, then you might let people go even though they do have cancer, right? So this is actually something that people look more for a diagnosis test. I mean, it's better to err on the safer side. If you don't have cancer and the test says you have cancer, maybe you'll end up having to do more diagnostic procedures. You might have to do some biopsy or something. But that's better than not figuring out some people. Right? So that's those are the two scores.
So you would want a more sensitive.
Yeah. So people in the health industry would want more sensitivity, which we call in the machine learning area, we call it recall. Yeah. And then there's something called the F1 score. And F1 score is something called the harmonic average of these two scores. Harmonic average of these two scores. And what's a harmonic average? It's like you take the reciprocal and you take the average. Okay, so it's like the 1 over F1 score is equal to 1 over the precision plus 1 over the recall divided by 2. So you can see that you're really taking the average of these two values as the reciprocal of the F1 value. That's how you're saying it, right? They're actually, you only know the usual average, right? A plus B over 2 is your mean. But that's the easiest mean. There's several things that look like some function applied to this value, function applied to this value, function applied to this value. The most widely used ones are when f is a log, that's called geometric mean. If f is squared, that has something to do with the velocity or something, or variance. Yeah, so you can have m squared equals to a squared plus b squared over 2. And these functions have different concavity, and there are some functions, some theorems on that, and basically what it means is this. This way of calculating the average punishes if one goes too far off. Then if these two values are pretty similar, the F1 score goes up. So this kind of likes, the F1 score likes to have these two things balanced. Right? See, that's the difference between machine learning people and people in the health industry. Health industry might just want the sensitivity to be high, but we really want the overall performance to be good. So we want these two to be somewhat balanced. And the way we make these two things to be balanced is by using the harmonic mean rather than the regular mean. Now you could also do the opposite. You might want to have a higher value when they're off balance, one is bigger than the other. Then you use this, forgot what this is. You take the square and then if you divide by 2, this gives you a better value if one thing's off balance, one is bigger than the other. Okay? All right, so that's called the F1 score.